Hello, everyone. My name is Misha, and today I'm going to be talking to you about how semi-definite programs simulate approximate message passing robustly. This is joint work with Sil Strom, also here at STEM. So before we begin, let's go over a few definitions. Let's understand what the problem it is that we're facing. In particular, let's first talk about what is approximate message passing. The problem that we're going to be studying in many different forms is going to be the following. We want to maximize some quadratic form where X is a given Gaussian orthogonal ensemble matrix. In other words, every entry is normal with mean 0, variance 1 on n. And we want to do this as a constrained maximization problem where the vector V lies in some feasible set K. There's many different options for this. For now, we'll keep it very general. A very popular approach for this over the past 15 years or so has been approximate message passing, or AMP. This was introduced by Donahoe, Malecki, and Montanari in 2009 for compressed sensing applications. It's been used for many others, some of which we'll discuss later, including the Sherrington-Kirkpatrick model, which was a recent development, and non-negative PCA, Planted-Klieg, sparse PCA, and many other things. At a high level, what is approximate message passing? Well, it's a generalization of power iteration. Whereas in power iteration, we just multiply by the matrix every single time. Here, we are doing some extra steps every time. In other words, we are approximately projecting to our feasible set K every time. We're kind of iterating between projecting and stepping multiplications. As an example, let's consider non-negative PCA. What is this? Well, the feasible set K here, it falls under this random quadratic optimization form. The feasible set K are unit vectors with non-negative entries. And the algorithm is actually deceptively simple. It's to choose these approximate denoisers, these approximate projections, which just do a ReLU on every coordinate. Right? The max is performed coordinate-wise, and we just iterate this. We take ReLU, we multiply, ReLU, multiply. And this turns out to almost give us the optimum solution. This was Montanari and Richard. So the fundamental question that we are going to be trying to discuss here is the following. Does AMP outperform semi-definite programs? In other words, for these kinds of problems, is the AMP approach strictly better? So as a negative for showing that AMP is better, Bandera, Kaminsky, and Wine in 2020 showed that the natural SDP for non-negative PCA exhibits an integrality gap. In other words, the first SDP does. And similarly, for the Sherrington-Kirkpatrick problem, Ghosh, Geronimo, Jones, Petechian, and Rajendran show that sum of squares, even at very high degrees, still exhibits an integrality gap. Here, the Sherrington-Kirkpatrick model has a slightly different feasible set. It's Boolean vectors. In other words, you could think of this as random max cut with Gaussian weights, because we're still taking our matrix to be Gaussian. On the other hand, though, even with these integrality gaps in mind, we know from the unique games conjecture that SDPs are worst case optimal for all constraint satisfaction problems. In other words, if the unique games conjecture is true, then we have optimality. Our question then is, can we extend this optimality to also be for average case problems, where X here is average case? Great. So this brings us immediately to our first result. It's that semi-definite programs can simulate approximate message passing. In particular, our main theorem is as follows, that we can construct an SDP, a polynomial size and associated rounding scheme, which can recover an almost optimal solution. So the caveat is we need to know low degree moments of symmetric polynomials in the samples. The samples here means the input X and what AMP outputs on X. So these aren't our exact X that we input. These are just samples to approximate moments of those. Right? So given that we have this AMP iteration, the denoisers are polynomials, we can output a vector which gets very close, like little o of 1 close, to the true optimizer, or a true optimizer that AMP outputs. As a corollary, if these denoisers are instead Lipschitz, which is a more common setting, for example, non-negative PCA, the ReLU operation is Lipschitz, then we can still do approximately the same thing modulo some polynomial approximation. In particular, for every delta, we can construct an STP, which has runtime depending on delta, and error, which depends on delta. As you can see here, it's additive error for some error in the exponent. This is great, of course, but it leads to two natural follow-up questions, so to speak. The first one is, AMP runs in nearly linear time. Essentially, if we consider a fixed number of iterations, t, here that's how long our AMP algorithm runs for, the AMP will run for time, say, n squared t, where n squared is just the time to multiply by the vector over and over again. Our STP approach, on the other hand, takes time very high. The exponent depends on the degree of the AMP final value as a polynomial. And so one question might be, this is a little bit unsatisfactory. What's the use of having this algorithm? And what do we gain otherwise for this runtime increase, huge runtime increase? The second question is more philosophical. I just told you about these STP lower bounds for non-negative PCA and Sherrington-Kirkpatrick, these like very strong lower bounds, in fact, for Sherrington-Kirkpatrick. Why are we able to circumvent them? What does our STP do that those do not? Okay, so given these questions, we are going to try and answer these and try and give a satisfactory answer. The first answer, the answer to question one, is robustness. That is what we gain. In particular, STPs have become a very useful tool for robust statistics. They've been used in many, many different places, too many places to mention: mean estimation, covariance estimation, linear regression, everywhere you name it, list-decodable regression, all sorts of these things. And natural STP hierarchies, such as sum of squares, have simple ways to encode these kinds of corruptions. In particular, if you edit some values in the matrix, there is an easy way to encode that. Our corruption model that we're going to consider here is called epsilon block corruption. In particular, the adversary can corrupt an arbitrary principal minor. In other words, they can choose a principal minor, which has epsilon and rows and columns, and arbitrarily change any of those entries. No care about spectrum. The intuition for this is by looking at the matrix as that of the graph. This is being able to arbitrarily change a block of the graph. This is a similar corruption model that's used in prior stochastic block model work. And this can already arbitrarily shift the AMP objective. For example, let's consider the very basic AMP algorithm, which just does power iteration. Instead of generalizing power iteration, just do it on its own. And let's consider the corruption, which adds a block of all ones to the corrupted section. This can arbitrarily, by epsilon root n, increase the operator norm of y as compared to x. X should have operator norm 2, while y should have operator norm epsilon root n. And we will see exactly that happening when we run AMP. You might also be wondering why we choose this principal minor epsilon block corruption model. The reason why is arbitrary corruption of an epsilon fraction of the entries in the matrix instead of just a principal minor is information theoretically impossible. And if you'd like to learn more, you can take a look at our paper. So given this answer, it turns out we can simulate approximate message passing robustly. The informal theorem is that for sufficiently small epsilon, we can basically get the exact same guarantees as before. We can construct this semi-definite program, poly-size, with an associated rounding scheme, which now takes in the corrupted input and outputs a vector which is close compared to whatever epsilon was, with high probability over x. Once again, this is polynomial time. And similarly, we get a corollary for the exact same result if we have Lipschitz denoisers, then we can do essentially the same thing, but with some extra loss in the exponent of the runtime to deal with the polynomial approximation. This is great. And it immediately tells us how we can do non-negative PCA and Sherrington-Kirkpatrick, how we can do robust non-negative PCA and Sherrington-Kirkpatrick, that is. As a first corollary for non-negative PCA, we can output a vector given a corruption of the input matrix, which gets almost the exact objective value. Root 2 is known to be the true optimum objective value of non-negative PCA given a Gaussian matrix X, and we can output a vector which is close to that. And the runtime of this algorithm, again, depends on delta, but for fixed delta, this is polynomial time. Similarly, for Sherrington-Kirkpatrick, we can also construct an algorithm which takes this block corruption y of x and outputs a unit vector, which gets almost the same as the optimum AMP value. So we're outputting a vector v such that v transpose xv is at least 1 minus epsilon times the optimum AMP value. Now, for this model, it's unknown yet whether this optimum AMP value is equal to the true optimum objective value for Sherrington-Kirkpatrick, but this is believed to be true modulo a fairly believable conjecture. And the runtime is, again, similar to non-negative PCA. So the application of this is we've kind of redeemed semi-definite programs. We've added robustness to these models while not sacrificing runtime. Now, given that, let's answer question 2. Why were we able to circumvent SDP lower bounds and do it in such a way where we could even add robustness? It turns out that the two are intertwined. And the key is that the lower bounds that I talked about prior are on certification algorithms. Not on all SDP-based algorithms, just on certification algorithms. To give an example, let's consider the natural semi-definite program for non-negative PCA. What is this semi-definite program? Well, it's saying, let's maximize over positive semi-definite matrices W, which also have all non-negative entries and trace 1. Let's maximize this inner product. Why is this useful? Well, a feasible solution is taking the true maximizer V and taking W to be VV transpose. And this will immediately give the optimum value. So by virtue of this, we know that this algorithm, this SDP approach here, it certifies that SDP, the value output by SDP of X, is at least square root 2, which is the true objective value. In other words, we can algorithmically prove it. Meanwhile, our algorithm does not do this. Our algorithm just bootstraps from the guarantees of AMP. We don't require any such problem-specific knowledge in this sense of the word outside of samples from the distribution. Another reason why certification algorithms should fail is because they will incorporate planned corruptions. For example, if I were to substitute X to be Y instead, where Y is the corrupted version of X, this SDP approach will certify the new value on Y. In other words, if we take some other true maximizer for Y now, the new SDP value must be at least the maximization value for that. And that's not good for us because, for example, we can have PCA, which gets arbitrarily worse. The objective value on Y is arbitrarily different from X. So that's why our algorithm can kind of circumvent these lower bounds. We don't require these certifications. Okay. As a summary of what we've shown so far, we can construct a black box SDP for any well-behaved AMP iteration, where well-behaved here essentially means polynomial, Lipschitz, anything close to that. And we can achieve the same objective value as AMP, not necessarily the true objective value, but the one that AMP provides us. We can extend this SDP to not just handle the base AMP input, but to handle corruptions which can arbitrarily shift the AMP objective value and still obtain an answer which is close to the original AMP objective value. The runtime is polynomial time when we have polynomial denoisers. But it depends on the degree of polynomial approximation for Lipschitz denoisers, which is not the worst problem in the world. It just adds a little bit. Great, that is the summary of results. So now let's briefly talk about how this works. In other words, let's talk about the proof outline. To do that, we need to introduce an SDP hierarchy called the local statistics hierarchy. Why are we doing this? Well, the main intuition for our algorithm, even though I said prior that we don't care that much about problem structure, well, we actually do. We encode information about it through these samples. And this provides an advantage over the natural SDP. We have this extra solution structure in mind. To that end, the local statistics hierarchy, it was introduced by Banks, Mahanti, and Raghavendra in 2020 in the context of the stochastic block model. And the key idea is to use the joint distribution of these input-output pairs, as you saw before, the input X and the AMP output V, together to determine feasibility. In particular, the original use case for this was for hypothesis testing between the stochastic block model and random graphs which don't have community structure. What's the idea behind the local statistics hierarchy? Well, it's to find a pseudo distribution, which I'll talk about in just a moment, a pseudo distribution which kind of says that all symmetric polynomials on our pseudo distribution must match the real values. In other words, where we had X and B, X is our input, V is our output, our simulation of what the AMP output should be, we require this to be equal to, or approximately equal to, the true output of AMP on a random matrix Z. Now, pseudo distribution here is just a fake distribution in a sense. It satisfies some of the properties. It satisfies having like the pseudo expectation of, and pseudo expectation is just expectation just under this new probability distribution of one being one, and that if we have a square of a polynomial, similar to sum of squares, if we have a square of a polynomial, then the expectation of it must be at least zero. This is what a pseudo distribution is, and this is all we require. We require that for all symmetric polynomials, we have this property. This is the local statistics hierarchy, and it takes in a particular degree and runs in time n to the power of the sum of the degrees, for example. So, with that in mind, what is our SDP? Well, first of all, in the non-robust setting, let's say we have no corruption, our SDP is just the local statistics hierarchy. We just give it samples from the joint distribution on X and the AMP output on X, and round out the resulting vector. Our program variable, as we saw before, right here. This program variable is exactly what we round out. The correctness of our algorithm then immediately follows from the correctness of AMP, because we are encoding through these symmetric polynomials the run of the AMP algorithm. This is already pretty neat. We're able to directly simulate AMP iterations, but we take it one step further with robustness. To add robustness, we add standard like sum of squares robustness constraints which enforce Y being an epsilon block corruption of X. Now the local statistics hierarchy we can use together with SOS style proofs and the proof system defined through all of these prior works to combine these two types of constraints, these pseudo expectations constraints and these robustness constraints. And together we can use those to essentially reduce down to the non-robust setting. That's essentially the proof outline, modulo many details coming about, which we encourage you to read our paper to read more about. Of course, there are some open questions that arise from this task. The first is, of course, efficiency. It's been hanging over us this whole time. The runtime of a semi-definite program depends on, exponentially, on the degree of the output of AMP as a polynomial. Even in the polynomial setting, even when the denoisers are polynomial, this is doubly exponential in the number of iterations. Now, AMP only runs for a fixed number of iterations, so this is polynomial time, but the question is, can we construct a faster spectral algorithm? That's one of the most important things we can do to make this efficient. The second open question is the dependence on epsilon. You might have noticed that we require epsilon to be sufficiently small. We require epsilon to be like little o of 1. It has to be 1 over polylog n for our result to make any sense. And a major question here is this inherent to this corruption model? Is this a requirement here for AMP, or can we still recover an optimizer when epsilon is, say, constant or bigger than 1 over polylog n? And these are two big questions that could make robustness more feasible. That's all I have for you today for semi-definite programming, semi-definite programs simulating approximate message passing robustly. Thank you.